Welcome to lecture here. We'll get started here in just a second. Go ahead and put here into the chat box roll. So we're going to continue on with chapter 10. And as you know, we do have a quiz today. So what we're going to do is we're going to lecture here for just a little bit. We're going to stop early. Then you could go take your quiz on Canvas using Proctorial. And then we'll have lab afterwards. So we'll do a little bit of lecturing. Again, we'll stop here early, probably a little bit, maybe around 11:15 or so. And you'll use the rest of the time there to go take your quiz. And afterwards, we will have lab like normal during our normal sort of time. We may start just a little bit later in terms of lab, but that's sort of the plan. So a little bit of lecturing here up front, stopping early, quiz, and then off to lab after that. And I think that's what we got scheduled here for today. Okay, so we've been talking about energy in this last chapter here. Remember that, energy, really a lot of times how we sort of deal with it is to classify what's happening in terms of energy as really one of two things, either an exothermic type of process where heat and energy is released, or an endothermic type process where heat and energy is absorbed. And as we talked a little bit about, I think last time as well, if it's exothermic, what that essentially means when we look at, say, something like a energy diagram that we saw earlier, that means that our reactants are higher in energy than our products. So they have to give off energy, which is sort of that exothermic part of it, to get to the products, and vice versa. For an endothermic, our reactants are lower in energy than our products. So in order to get up there to our products, they have to put energy in. And again, that's more of an endothermic type process. And in terms of values, as we'll see in this chapter, and I think as we talked about as well, if something's sort of exothermic in terms of heat and energy, if you calculate it, it will usually give you a negative value in terms of the value for energy. If the process is more endothermic, when you actually calculate, which we'll do some of this here coming up, you will get more of a positive number. So there's two sort of values that we commonly see that we'll talk about here coming up. Delta H, which is the enthalpy. Again, if that delta H value, as we will see, is a positive number, it means endothermic. If it's a negative number, it means exothermic. And Q, which is basically heat or energy as well. We'll do some calculations for that. And same deal, if you get a negative value for Q, that's going to be exothermic, and a positive value will be endothermic. So I think where we left off was right about here when we're talking about sort of energy and the first law of thermodynamics and thermodynamics in general. Basically deal with the idea is whether or not under certain conditions would we expect a reaction to occur. And the first law of thermodynamics deals with energy, and it's the conservation of energy. So we don't lose energy in any type of process. We don't gain energy in any type of process. So there's sort of a conservation of energy overall in the universe. But we do have that energy sort of transferring from one place to the next. And again, a lot of times when we think about sort of what's happening in terms of energy, we think about it in terms of the system, which is typically whatever we're dealing with, and the surroundings, which is typically everything outside of that. So for example, if you're doing a reaction in a beaker, the system would be the beaker, and then the surroundings would be everything pretty much outside of that beaker. So a little bit about internal energy, and we don't really get into a heck of a lot really on this stuff here, but just to kind of cover it here, the change in internal energy, which is delta E, is equal to Q plus W. Q again here is heat. So when we see this Q value here represents heat, and as you can see below there, W represents work. So a lot of times we do use energy to do some type of work on something. Our work is being done on something else, and the change in internal energy is the sum really of the kinetic and potential energies of a particle in a system. Again, kinetic energy is the energy due to motion. Potential energy is the energy, kind of stored energy, if you will, the energy due to sort of its position. And again, that classic sort of example of a big giant boulder on top of the hill has a certain amount of potential energy, it can go over the hill and start moving down, which would transfer it to kinetic energy. So that's sort of what we're talking about here. Same sort of convention here with the E in terms of energy, to change in internal energy. Again, usually negative means more of an exothermic, and positive means more energy is being absorbed, endothermic type of representation. So again, we talked a little bit about this, but just to reiterate, if we calculate Q, which a lot of time in this class, we will deal with mostly Q. And when we do calculate Q, again, that positive value means endothermic, and that negative value means exothermic. And the idea here is, as we talked about, for example, if this system lost 5 joules of energy, it would be negative for the system as it is exothermic, it's losing that energy. When we talk about sort of the surroundings out here, the surroundings would gain 5 joules of energy in that sort of example. Again, here, the actual value or number will be the same. The only sort of difference here is the sign to sort of reflect whether or not the energy is being given off or being absorbed. And again, this is sort of that idea as well, that conservation of energy. So although the system lost that 5 joules of energy, it wasn't completely lost and gone forever. It was absorbed by something else. In this case, the surroundings would gain that 5 joules of energy. So again, for us, we'll see Q a lot, and it's good to understand and have that idea that the positive value means endothermic, absorbing energy, negative, exothermic. In terms of work, again, we don't do a heck of a lot with work in sort of this class. You'll probably cover it a little bit more in, what do they call it class here? 1A, I think. But the sign as well. So work is basically, something that's being done, sort of force over distance. And same idea, if the system is doing work on the surroundings, it's negative, almost sort of the same idea as it exothermic, if it's releasing energy, being negative. And if the surroundings is doing work on the system, it would be positive. So the work sort of being done on the system as well. And again, sort of the same classification. So for us, probably not worry about too much in terms of work or anything like that. So in an endothermic process here, again, Q would be heat. And again, for our purposes, Q would be a positive value. And work is done on a gas, and the process is exothermic. So if work is being done on the gas by the surroundings, then that would be positive for work. Again, if the process is exothermic, then the Q value or the heat value would be negative in that case. So let's talk about some important units, though. When we do talk about energy, really, there's 2 sort of big units that we commonly come across, and these are them here. This is calories and joules. And the definition of a calorie, and one thing about this calorie is it is actually a lowercase c, and that's important because there's also another calorie that's a capital C. So you'll see calories as with a capital C, and you'll see calories with a lowercase c. So usually in chemistry here, we usually deal a lot with the lowercase calories, and a calorie is basically the amount of heat that's required to change 1 gram of water by 1 degree Celsius. A joule is also another unit of energy that's used a lot. Also, sort of the kilo versions of these guys are also used a lot. Kilocalories is used a lot. A kilocalorie is 1,000 of our little calories. Also, kilojoules is used a lot, and that's 1,000 of our joules. So that's a very common sort of unit of that. So with this calorie with the capital C is a nutritional calorie. And basically 1 calorie with a capital C is the same as 1,000 of the little calories with the little c. And that's the same as 1 kilocalorie. So, if you've ever been on like a treadmill or anything like that, sometimes where they show the calories, they'll show how many kilocalories you're burning. And again, that's sort of a nutritional calorie, which is the capital C. So again, the capital C does so usually represent that nutritional calorie. So usually here we do really deal with the lowercase c. And this conversion here, you do need to know, as the big arrow says, I suppose. This is the conversion to go from calories to joules. And in 1 calorie, there's 4.184 joules. And that is definitely a conversion that you use a lot in chemistry, especially in what we're going to be talking about here, which is sort of specific heat. It's used a lot. So here, if we wanted to convert 60.1 calories into joules, we could use that conversion factor to do so. We could use dimensional analysis as well. So here we would start with our 60.1 calories. This is our conversion factor that we just had. Again, the calories are going to cancel each other out, going to leave us with joules, and we end up with 251 joules. Again, in terms of significant figures, we would be defaulting back to this guy here, as with this guy is a conversion factor here, so it's an exact number, so we don't have to worry about it. So here we have 3 significant figures and 3 sig figs on this guy here as well. And again, that's a very common conversion that you have to do a lot, especially when you're dealing with things like specific heat and stuff like that, going from calories to joules and joules back to calories. Now, the heat required to change the temperature does depend on the substance, and the amount of the substance, or the number of grams, the temperature change, and the identity of the substance. And there's something, as we will see here in just a second, which is known as the specific heat capacity. And the specific heat capacity really is the amount of heat required really to change 1 gram of a substance by 1 degree Celsius. And that's why specific heat capacity, as we'll see, I think on the next slide perhaps, has units of joules per gram per degree Celsius. Our common units are calories per gram per degree Celsius. And again, it's basically the definition there, the energy, like joules, required to raise 1 gram of a substance by 1 degree Celsius. So that's why it has all 3 of these sort of units associated with it. And again, it is that amount of energy that's required to change that substance by 1 degree Celsius per 1 gram. That means if you think about it, if you have a larger value for the specific heat capacity of a substance, it takes more energy to convert or change the temperature by 1 degree than if you had somebody that had a smaller one. So if you had somebody that had 0.25 joules per gram per degree Celsius, versus somebody that has specific heat capacity of, say, 3.2 joules per gram per degree Celsius. It would take a lot more energy that need to be put in there to change the guy on the right there by 1 degree Celsius than it would the substance there on the left in this made up example. Again, on the left, you just need to put in 0.25 joules of energy per gram to raise it, while the other one you got to put in about 3.2. So you can look at something like the specific heat capacity of a substance, and it can kind of give you an idea as to whether or not, do it to take a lot of energy to change the temperature or not. So for example, water, liquid water. So liquid water has a specific heat capacity of 4.184 joules per gram per degree Celsius, hence where that conversion comes from. And we also have 1 calorie per gram per degree Celsius. So this is specific heat capacity of liquid water. And a reminder as well that what we will see in some of these examples is when you do look up the values, these are typically values you can find in a table, you do want to look it up for not only what you're looking for in terms of the substance, but you do want to look it up in terms of the actual state. And water is a very common one that you come across as you need to look up. But for example, if you had something like ice, which is also water, but is water in the solid state, the specific heat capacity for something like ice is like 2 joules per gram per degree Celsius. So it does change depending on the state of it. And again, you'll see a table. I think we have one in here. If not, you'll have to see one in your book. But you do want to make sure that what you're looking up for is not only, the right substance, but also the right state it's in, solid, liquid, or gas, when you go to that table. And again, sometimes people just grab like the first one they see in the table. Oh, that's water. I'm not really sure what state it's in, but we'll just go with that number. And you do want to make sure that you do get the right state. This is probably also some numbers here, the 4.184 and the 1 that you should know as well, which is a specific heat of water. And like I said, that's one that's used a lot in chemistry. And here is that table. And as you can see, when we do water, which is ice, a very different number, and even gas is actually a slightly different number. So really important when you go to the table like this that, again, you take a look at the states of those guys and make sure that you get it. We see some things like some solids over here. We got some silver, some gold has 0.24. And you can see on this table, just looking at these values, you can see water has a pretty high specific heat capacity. And that's why it actually takes a lot of heat to change water by 1 degree Celsius, which is why typically if we have a pretty large body of water, like our oceans and stuff like that, it takes a lot of energy to actually change it by 1 degree Celsius. And when you do start to see, the temperature, for example, of the ocean and stuff like that change by, a degree Celsius or 2, you may think to yourself, doesn't seem like a lot. But because water has a very high specific heat capacity, to get water to change by even 1 degree Celsius means that there must be a lot of heat there to allow that to happen. And that's sort of the idea right behind things like, global warming and stuff like that. All right. So again, calories as well. And I would say also probably in most cases, though, we will see mainly joules, but you will see some problems involve calories. So very common, people would kind of use the unit as joules, but calories as well does pop in there. And again, as the big arrow says, you do need to know that value there of the 4.184 and the 1 calorie per gram per degree Celsius. And again, that's specifically for liquid water. Now, there is a formula that we use, and it's sometimes referred to as a specific heat formula. And this is the formula that's used to calculate the amount of heat required, to change a substance in terms of its temperature. So this formula is used when we have a substance that's in the same state. So for example, it's liquid all the way through, but we decide to change the temperature of it. So, we want to take it from, say, 20 degrees Celsius to 60 degrees Celsius, all still the same liquid in that sort of area. And this is Q is equal to MS delta T. The Q here is heat or energy. And again, it has typically units of joules or calories, depending on sort of which one you're going with. S is our specific heat capacity, which we were just talking about, and it has units of either joules per gram per degree Celsius, or again, calories per gram per degree Celsius, depending on which one you want to choose. M is the mass, and it has units of grams, as you can see down there. And delta T is temperature. And this is one of the few formulas in chemistry where you actually do not need to change the temperature to Kelvin. So you can actually usually leave it in degrees Celsius, but it is in degrees Celsius. And the reason it's in degrees Celsius is pretty much our specific heat capacity has degrees Celsius, so all the units will cancel. Now, the important part about delta T is not just the temperature, but it's actually the change in temperature. And what that really means is when you do delta T, you want to take the final temperature minus the initial temperature. Now, the truth is, if you didn't take final minus initial and you just took the difference of the temperature and you put all the numbers into this equation, you will get the same answer for Q, regardless of sort of if you did final minus initial or just did larger minus smaller. But it's really important to actually do final minus initial. And the reason for that is when we look at specific heat capacity, this is a positive number. When we look at the mass, it is also a positive number, which means what truly determines what is going to happen in terms of Q. And what I mean is, will it be a negative value or a positive value, is actually this part of it, the change in temperature. So if our temperature started at 20 degrees Celsius and went to 60 degrees Celsius, the temperature increased. In order for the temperature to increase, you have to put heat and energy in. and then we will see a reflection of the temperature go up. And that should be an endothermic process, and that means our Q should be positive. So here, if we did final temperature 60 minus initial temperature 20, that gives us a change in temperature of 40 degrees, which is positive. And we would end up with a positive Q. And as we've been talking about, positive Q means endothermic, which is what we would expect. Now, if the opposite was true and our temperature started at 60 degrees and we threw it on ice and we ended at 20 degrees, when we do our change in temperature, it technically should be 20 minus 60, which gives us minus 40 degrees in this example. The minus part here, because the rest of these guys are positive, will turn our Q into a negative number, which means it would be exothermic, which is also what we would expect it to be in this situation. The only way the temperature could go down is it has to release that heat and energy, and it does go down. So sometimes when people are taught this equation, they're taught just take the larger number minus the smaller number, which numerically speaking, you will get the same value. But it is really important to make sure that you do the change in temperature as final minus initial, because again, that's going to give you the correct sign, either positive or negative, when you do this equation. Any questions on that there? So obviously this equation, you do need to know obviously how to use it. And let's take a look maybe at an example here. All right, so why don't you take a second here, calculate the amount of heat and energy needed to raise the temperature of 6.25 grams of water from 21 to 39 degrees Celsius. Let's see what you come up with. Okay, so here again, we're going to use really that Q is equal to ms delta T. We do have M given to us, not given to us, which is specific heat capacity here of liquid water, we're assuming. So remember that S is 4.184 joules per gram per degree Celsius. Or again, it is 1 calorie per degree per grams. But here we are looking for joules, so we might as well obviously use this version of it, which means we do have this. And we do have our two temperatures here as well. So obviously we just need to plug it in. So our mass is 6.25 grams. Our specific heat capacity, joules per gram per degree Celsius. And again, here we want to do our final temperature, which is 39 degrees Celsius, minus our initial, which is 21 degrees Celsius. And if we do all that good stuff there, we do end up perhaps with something like 471. And the units would be grams would cancel, degrees Celsius would cancel, joules are the only unit that is left there, and we would end up with joules here. Any question on that particular one there? And in terms of sort of sig figs, we're multiplying there. So we got 3 sig figs on that one, 4. And then actually when we take 39.0 minus 21.0, that's 18.0 technically the number should be. which is also 3 significant figures. So probably should end up with 3 significant figures when it's all said and done. Again, ultimately, the last thing that you did was multiply all the way across. And everybody had 2 of them had 3 sig figs, and the guy in the middle there had 4. Any questions on that particular one? Also, we see that the temperature went from 21 and increased to 39, which would imply that this should be endothermic. And we do see a positive value here for Q, which also tells us that it is endothermic. So all that does make sense, you know, in terms of the sign and everything that's going on with this one. All right, so hopefully they agree with me. That's a lot of slides to this example. There you go. All right. So they round it off. They put the little line, but round it off to 471. It'll be fine. All right, try this one here. A pure sample of iron requires 142 calories of energy to raise the temperature from 23 to 92. What is the mass of the sample? Specific heat capacity of iron is 0.45. So see what you come up with. Okay, so on this one again, we're going to use our formula here. Q is equal to ms delta T. We have 145 calories, and that would be Q, 142 calories. We do have our final and initial temperature being 23 degrees Celsius, final temperature being 92 degrees Celsius. And we do have the specific heat capacity given to us, which was 0.45 joules per gram per degree Celsius. So we just kind of tick off here. We have these guys. We need to solve for mass. We do have a little bit of a conversion problem here. Our Q is in calories, and our specific heat capacity here is in joules. So we do have to do a conversion. So you could do either one. You can convert the specific heat capacity into calories if you want, or you can convert the Q into calories. So here I'm going to convert the Q into calories. So that's 142 calories. And again, there is 4.184 joules per calorie. And if we do that here, 142 times 4.184 gives us something like 594 joules. Technically, you should go to about 3 sig figs on that. If you want to keep a digit there, you can until the end. At this point, we could solve for M. M would equal Q divided by S delta T. And in this case, 594 joules we just converted. Our specific heat capacity, which was in joules, so all that should work okay. And again, here our change in temperature should be our final minus our initial. So we're going to do a 92 minus 23 degrees Celsius. So degrees Celsius will cancel, joules will cancel. When we do the dividing, the grams will come up on top there. And if we do that, divide it by 0.45 and divide it by 92 minus 23, looks like we should end up with probably 19 grams in this case. And again, in terms of sig figs, I kept the whole number. There's like 0.1, whatever it is on the joules, but technically this should be 3 sig figs. This guy is 2 sig figs. And I believe when you subtract these guys here to the whole number, you also end up with 2 sig figs. So 2 sig figs there on the answer at the end. Question on that? Okay. All right, so try one more here. The specific heat capacity of lead is 0.13. How many calories of heat would be required to raise the temperature of 150 grams of lead from 25 to 100 degrees Celsius?
Yeah, I've got a question.
Yeah.
It was just about the other one.
Yeah.
So did you just switch the formula around to get to how to find mass?
Yeah, so this was like kind of the original formula up here, the Q ms delta T. So basically we want to solve for M. So we want to divide the S and delta T to the other side.
Okay.
And then they cancel, and then you're left with what we got down here.
All right, thank you.
You're welcome.
Can you please show the next example?
Yeah.
So I can write it down. Thank you.
There you go. Okay, so here again, using our Q is equal to ms delta T. We do have our S given to us, which is our 0.13 joules per gram per degree Celsius. We do have the M given to us, which is our 150 grams. And we do have here our initial temperature, and this guy here being our final temperature. So really, we do have everything sort of on this side to calculate Q. So we could actually just put it in there. So Q would be 150 grams. Our specific heat capacity, 0.13 joules per gram per degree Celsius. Again, doing our final minus our initial, which would be 100 minus 25 degrees Celsius. And if we do all that good stuff there, 150 times 0.13 times 100 minus 25. And that gives us an answer of about 1462.5. And in terms of the units here, Celsius councils, grams council, we're left with joules at this point. In terms of sig figs, just to think about where we really should be on this number, this guy's got 4 significant figures. This guy's got 2 significant figures. And when we subtract that, that should be 75, which would also be 2 significant figures. That technically means that our answer should end up right about here at 2 significant figures. Although we're not really looking for joules either, we're actually looking for calories. So if you like, you can just hang on to that number for now. Do the conversion of 4.184 joules per calorie. And the joules here will cancel. And if we do that, we do end up with something like 349.54, a whole bunch of numbers. Calories, again, we still should end up probably at 2 significant figures. So probably something like 350 calories. We want to kind of clean it up at the end. If you kind of cleaned it up earlier there, you might get a slightly different number. You'll get something like 359 calories if you sort of rounded this guy really strictly to 1500 at that point and then did it. You'll end up with something like 359. Again, most time you probably want to just kind of carry the numbers to the very end and clean it up at the end. But if you did round 1500, it'd probably be okay if you got the 359, which technically you then should round to 360, I guess it would be on that case.
I have a question. Isn't the final 100? Wouldn't this be a negative number?
The final is 100, but when you do change in temperature, it's final minus initial.
Oh, okay. Thank you.
And so we do get a positive number for Q here, which is what we would expect because it should be endothermic because the temperature started at 25 and it raised to 100. So the only really way to do that is to put heat and energy in, right? So it will raise the temperature. If it was opposite and we ended at 25 and started at 100, energy would have to be released and be exothermic in order for that to occur. Other questions on this?
Yeah, I've got one. So are you able to just convert the 0.13 joules over grams to calories in the beginning?
You could do that too. That's another option. You could do that. You could convert the joules per gram per degree Celsius there, the specific heat capacity into calories and just plug it in. Again, probably with rounding, it should be in, hopefully it's kind of the same ballpark in terms of the final answer. But you absolutely could do that as well. Yeah. Other questions? Yeah, so you would probably be okay if you rounded that to 1500 and then continue on with the 1500. I would be able to figure it out, which you did. And as long as the final answer, again, if you did that 1500 and you got down to the final answer, you would have had something like 358.5. You would have needed to round it out to 2 significant figures, and then you would be fine in terms of significant figures, which I guess would be 360 at that point. Other questions on this particular one? Okay. So I think what we're going to do is we're going to stop here right now for lecture. And we'll just talk a little bit about what's going to go on now. The quiz is going to happen. So in just a couple minutes, I'll make the quiz available up on Canvas. The quiz will be on Canvas, so you'll take it through Canvas. You will need a piece of paper to do some work and show some work. So you could get some partial credit just in case something goes bad with the answer. You could use a calculator, again, no notes or anything like that. You do have to use Proctorial. So you do have to, just like the practice quiz, that means you have to use a computer, a webcam, and obviously Chrome with the Proctorial extension in there. If it asks you for a code for the quiz, that means that something is not correct. You're not using a computer, you're not using the Proctorial, or you're not using Chrome. So it should not ask you for any type of access code. If it does, it just means your thing is not set up right. So that's why we did the practice quiz. So hopefully you got that all worked out and it shouldn't be a problem. A reminder that there is an end time for the quiz. So if if you start right when it's available, you should be fine in terms of not running out of time. If for some reason you decide to wait, which you should not do, you should start as soon as it's available. And the computer cuts you off, I will not reopen that quiz for you. Yes, so make sure you start it. Once you hit submit, your quiz will be submitted. So there's only one submit button at the very bottom. So only hit it when you're completely done with the quiz, and then hit the submit button. If you hit it before you answer all the questions, it'll actually put a warning up like, are you sure you want to do this? And the answer should be probably no. Yes. So you do need to show work on problems that say you need to show work for it. They're clearly labeled, and those should be done on paper, which needs to be uploaded after you submit the quiz. It is in its own module. Yeah. So you'll see it'll call like taking quiz 1 module. It's a whole thing. And you will go to that module and you got to do it in order. So the first thing you have to do is look at, there's an academic honesty agreement. You need to sign the academic honesty agreement. There's kind of an electronic version of it. You could either print it and sign it, the paper version, or the electronic version, type in your initials, good enough. And then it will open up the quiz. You take the quiz using Proctorial. Once you're done taking the quiz, you need to submit your work immediately after you submitted your quiz. If you wait too long to submit your work, though, you will not get any points for those questions. It's not like submit your answers online and then decide, oh, I remember how to do that later. You will not get points. So you need to submit that immediately or you will get 0 on those things. And other than that, I think that's pretty much everything that you need to do. Whatever you need, I think, should be on there. You don't need a periodic table, so one was not provided for you. If you need a periodic table, you're doing something wrong, I think, on this quiz. So you don't definitely need one. And make sure that you do take it. A reminder that if you click away from the quiz, I wouldn't do that. But if you click away from the quiz or the quiz closes or whatever, you can log back on. But a reminder that the timer will not stop. So as soon as you hit start, make sure you're ready to take it. Other than that, any questions on that? Again, what you will see is in just a second when we're done here, there will be a whole module that will open up. And again, you got to kind of go in order. Faith, did you have a question? Or?
Yeah, I did have a quick question. Is there a specific way that you would like us to face our camera for Proctorio to see us besides facing our
Yeah,
face?
I would appreciate it if you could kind of do it. That shows obviously you and your work area. If you could kind of get that, so I could kind of see what's going on in your work area as well. That would be perfect. And also kind of see you as well. So that kind of combination with your workspace and yourself would be perfect and stuff like that.
Got it. Thank you.
Thank you. Other questions? Okay, so in terms of lab, we do have lab today. So what we're going to do is we're going to start lab just a little bit later. We'll start at 12:15, give everybody a chance after they take the quiz, get up and walk around and all that. And then we'll do lab at 12:15 through the lab link. And then, so I think it's physical chemical changes part 1 or something like that is the experiment. And we'll do that experiment at about 12:15. We'll log in for that. Just give everybody a little chance to not have to run from one thing to the next and stuff like that. Any questions on anything else before we go?
I have a question.
Yeah.
So what specifically, what sections are going to be on the quiz, or what formulas do we need to know?
So all the formulas there that we talked about is specifically, I believe, just this is chapter 2, I believe, in your book. Yeah, chapter 1 was nothing. So it's all supposed to be whatever we covered in chapter 2. It's fair game. So I think only in chapter 2 you pretty much had density. I think it was the only formula I think maybe that you had, and a reminder that the temperature conversions will not be given to you, and you do need to know those guys as well. Other questions on anything? Okay, so give me about a minute or so, then it should be up there. There'll be an announcement that will come out on Canvas with a link to link you to the quiz. And then again, like I said, you'll have to do the academic honesty thing. There's a PDF file. If you want, you can print it and sign it and upload it. Or if not, you just need to go to the next one, which is the electronic version where you can kind of sign it. That will open up the quiz, and then that will open up your you're uploading your work. Remember as well, one last thing, that there are different versions. Yes, so like a normal quiz, don't have the right answers on the wrong version or anything done like that. That's going to have to make me give you a 0. And your answers that you submit online do need to match the answers that you upload as well. All right, good luck on your quiz. And like I said, in about a minute or so, you'll see an announcement through Canvas and it'll have a link to it. Otherwise, it will be in the module section and it will say something like taking quiz number 1. And again, I'll see everybody at 12:15 for lab to start. And if you didn't put here for the roll, make sure you do that before you log off.